I hope to do one of the more fundamental parts of the course, namely tying everything together and showing you that most of the stuff we spend so much time constructing over the last few weeks actually translates directly to the bulk of modern contemporary machine learning, namely deep learning. To do that, I first have to say what I mean by deep learning, because it's such a big word by now, right? Filled with all these different concepts from, depending on who you ask, something like Rosenblatt and the perceptron, all the way to transformers and large language models, and this is all supposedly the same thing. So what I'm trying to do today, at the outset, is to define a generic notion of what deep learning might mean as a word, still reasonably precise, with the goal of having a generic description that applies to everything that I want to do afterwards. And actually, I think also applies to pretty much everything you might do with a deep learning library. So for my purposes, for the purposes of this lecture and the one next Tuesday, a deep neural network is a differentiable program. A differentiable program to me is a second order function, a bivariate function, that I write specifically with this sort of functional programming style notation with two brackets, in the sense that it's an object which you instantiate on a set of parameters. They're called theta. There is d of these parameters. And then what you get back is a function that you can give an input to. That input is called x. It comes from some space, whatever. And then it returns a multivariate real-valued function in general. So here's a picture for that. I give you a set of parameters, and then I get a function that I can evaluate on arbitrary inputs. The most important thing to understand for today is that there are going to be these two objects, and once I fix the parameters, there is still a function left of the inputs. And when I later on will say that I will make the function linear, I will usually mean linear in theta, not in x. Right? Because the entire point of a powerful AI system is that the resulting function is very nonlinear in x. I will also, so the typical structure is, people talk about deepness because they're thinking of some kind of hierarchical structure like this. There is, the parameters theta consist of a data structure, some kind of pi tree that contains lots and lots of layers and weights and biases. You were thinking of this function as taking the input x, and then you do an affine transformation, so you scale linearly and add some shift, and then you do some nonlinear transformation, whatever it might be, some VLOOS, something interesting, some CLOOS, some tan-H transformations, whatever. These linear transformations here might be something complicated like a convolution, right, and a pooling and so on. And then we keep doing that for a few more times, and then at the end you get an output. So that's why we use the word deep, but really actually for the purposes of today, this hierarchical structure won't even be that important. There's just going to be a set of parameters and an input, and that gives us an output. And the other thing that I will assume is that we can compute gradients of this function with respect to theta for arbitrary inputs and outputs, y and x. That's why it's called differentiable programming. That's the word that Jan LeCun uses. And I guess you will agree with me that pretty much every architecture you might use has these gradients, because otherwise you can't do deep learning, right? You can't do training if you don't have a gradient. OK, beyond that, I will not assume anything further about the structure of this function. I will not assume it's a convnet or a multi-layer perceptron or a transformer or whatever you like. If you want to hear a course about the structure of these models, you need to go to the deep learning class by Andreas Geiger or someone else. By the way, I will also occasionally show some code. And this is sort of my mental picture of what a deep neural network is. Looks something like this. And here it's maybe interesting. When I show you this code, I mean, partly because we can just, it looks like, oh, it's actually code. It's not just some mathematical idea. But also, I think we're now at a really interesting point in the development of the software stack of machine learning. There are now some established frameworks for deep learning, PyTorch, for example, right, which are pretty much universally used. And they have imprinted some kind of idea of what deep learning is on the world. Some design choices have become sort of solidified and cemented. And one of the reasons actually why I use JAX for this course is not because I fundamentally think JAX is like the better way to do deep learning, but I get the sense that it's still a much less mature framework, right? It's still in 0 point something version land. And you can tell using it that it's written by various different groups of people competing with each other for the for the interpretation, right, of the design authority on how to write a deep neural network, for example. In JAX, there are actually, I've lost count, at least 3 or 4 different libraries for deep learning, because JAX itself is just basically a tunnel out of Python into a fast C implementation. And people have built modules on top. One of them is called Equinox by Practical Culture. And this is at least an early version of how you would write a multi-layer perceptron in Equinox. By now there are more modules, so there's an even more compact way of writing a multi-layer perceptron. But it's a class that contains a data structure called layers, that contains all the stuff that you need to know, the parameters and also the structure of those, like how many layers there are and what kind of, how they are connected to each other. And then there's a constructor which initializes the network immediately and then defines how to evaluate, how to construct the architecture, and then you can call the function afterwards. So here you really see this second order function structure that I just had on the previous slide, right? The constructor is the thing that makes the parameters theta. Once you have that, you then get back a function that you can call on an input x, and it returns some output, right? Some value. And it has this weird recursive structure here. So how do we train such deep neural networks? Again, this is not a deep learning class. I'm just trying to abstract away so that we're all talking about the same idea. Training deep neural networks is regularized empirical risk minimization. And I say regularized empirical risk minimization because I once had a nasty conversation with a reviewer who said, there is the deep learning is not regularized, or deep learning is regularized, or whatever. In general, you will have a regularizer, and that regularizer might be 0, then it's just not regularized. So to train a deep neural network, mathematically speaking, what you're doing is you're finding a set of parameters, theta star, that minimize a loss function, right? And by the way, you can not vigorously, then I know that you're following. So a loss function typically contains a sum over individual terms, where each term depends on the entire neural network, so all the parameters, and one datum, one pair of inputs and outputs, xi, yi. By the way, this actually also applies to unsupervised learning. You can think for yourself about how that would look like in unsupervised learning, but there's still going to be a loss function for every individual input, xi. And then there's just no yi. For example, if you have an encoder-decoder structure, you're just constructing the yi directly out of the network, right? So these individual terms are sometimes called risk, empirical risk. They contain the network contains the parameters in the input, and then there is some training output. And then there may be a regularizer. So on Tuesday, on Thursday, we already spoke about the first connection of this framework to Bayesian inference, which is that it turns out both the regularizer and these empirical risks actually have Bayesian interpretations. The typical loss functions you encounter in a standard setting in deep learning are usually something out of these 3 choices. So if you have a binary classification problem, you might use a logistic loss function. So this looks something like this. And when you first encounter a function like this, you might not think of probabilities. It's just some weird thing, cross entropy, right? But we've now discovered that this is actually exactly the logarithm of a posterior, the logarithm of a likelihood in Bayes' theorem, which arises. So I should explain why I say likelihood. Okay, let me first do this. So we can write this like this. We notice that we can think of this sigmoid of f as in such a sense that f becomes a log odds, so the logarithm of the ratios between the probabilities for the output class and the other class. And why is this a likelihood? Well, because in here, in f, we have the parameters theta hidden away, right? So if we think of this as a function of theta, then it's a likelihood for theta, for the parameters. I actually wanted to have them here on the slide, but then the equations would become too wide, so I took them out again. Similarly, if you're using a softmax loss, so the logarithm of a softmax, sorry, that's the multivariate cross entropy loss, then the exact same thing holds. It's just log odds between all the classes. And of course, for regression, there's L2 losses, and L2 losses are just the logarithms of Gaussians, of basic Gaussians, right? So I hope you're still following. We've made the connection that loss functions in deep learning are just log likelihoods for the parameters of the network. What about the regularizers? So there are various regularizers in use now, depending on which one you like. There's I think sort of emotional attachment in some research groups to things like dropout or various other forms of regularization. There's also disagreement over what a regularization actually is. Is batch norm a regularizer, or is it a part of the model, right? So these are technical considerations that I won't be getting into. Let the engineers worry about that. For a most basic example might be an L2 regularizer. So something like this added onto your weights. And then people do all sorts of weird things during training, like they might decay the regularizer, so they let go lambda to 0 during training. You can wonder about why that is. For us, mathematically speaking, it's convenient to realize that we can think of this, because it's a function only of theta and not of the data, as the logarithm of a prior. And an L2 regularizer would be a logarithm of a Gaussian prior. Okay, so far? So we've learned that when we do empirical risk minimization, we're actually doing maximum a posteriori inference, if you like. We find the mode of a posterior. Now, you can have all sorts of debates about whether that's actually a meaningful posterior, whether this L2 regularizer was ever meant to be a prior, right? And that's totally valid as a discussion. I would actually argue that these L2 regularizers are not meaningful priors, because no engineer sits down and says, my Gaussian prior on the weights with 0 mean. And no, of course not. It's just a regularizer that you decay to 0. But from a mathematical perspective, they have the exact same form as a posterior. So if it's only just about defining a well-defined probability distribution, then things work out. This will give a posterior on theta, if you take the exponential of this loss function. And then you can have a philosophical debate about whether you think that's actually a meaningful philosophical object, or it's just a probability measure that has no meaning. And if it has no meaning, you have to go back to the engineer and say, why did you use this stupid distribution? Right? It's not a problem of probability theory if the users make silly assumptions. Just also, again, to drive home this point, this is what a loss function looks like in an example implementation from Equinox. So you use a library that contains the losses, right? So there are optax losses.sigmoid binary cross entropy. The reason I'm showing you this is that I think now that the software stack has grown to include all of these helper functions, the implementation gets a lot easier, because you don't have to constantly write these functions yourself. They're also sometimes a bit more efficient. They come with autodiff and so on. It's all nice. But they increasingly hide all of this mathematical structure. It gets ever harder if you don't have a class like this one to look at this piece of code and realize that you're still doing the same Bayesian inference that people did 70 years ago, just totally souped up to run on super complicated hardware and huge parameter spaces. So now, let's do it the other way around. So now we've started the sort of the connection to deep learning by talking about what a deep neural network is, and then drilling down to how its connection to probabilistic inference is. Now I'm going to turn around and change modus operandi and go back to what we did in the class, starting from lecture number 3, learning functions, and just recap something that I already showed you a few times to make an actual connection between these two frameworks a bit more precise. So in regression, and we talked about first Gaussian parametric regression and then also Gaussian process regression, we also encountered one of these higher order functions, x, a function of x and parameters, inputs and parameters. And there we made a very specific assumption that the function is linear in the parameters and non-linear in x. We made that assumption because it made the computation easy, because it reduced everything to linear algebra. We we also made a few interesting observations along the way. For example, we realized that we can make this a function of pretty much anything in x. So x doesn't need to be real valued. It can be strings, it can be graphs, it can even be functions. There are now operator valued functions that take in functions and return real numbers or outputs that are also function valued and so on. So in x, we are very flexible. We just have to assume that we are linear in theta so far. And that's the one assumption we're going to jettison today. So because the function was linear, we got away without approximations. We got away with by making specific choices for prior and likelihood, but otherwise we didn't need to do any approximations. What we did was we said, let's put a Gaussian prior over the parameters of this model, a Gaussian on theta with a general mean and a general covariance. You're now noticing that that's very familiar to the regularizer in deep learning. And then we use this likelihood, which we now know is the exponential of a loss function. That was also Gaussian because we were looking at regression problems where the observations y are also real numbers. If under this choice, so linear function, Gaussian likelihood, Gaussian prior, Bayes' theorem is closed form, or let's say it reduces to linear algebra, and the posterior is also a Gaussian distribution with a mean vector and a covariance matrix that are given by, well, linear algebra expressions. So they're just multiplying vectors and matrices and solving linear problems, inverting matrices in big quotation marks, big scare quotes, because of course, as we learned, you don't actually want to compute the inverse of a matrix, you want to solve a linear system, use an algorithm that solves a linear system. So one interesting observation that I actually mentioned already when we did regression, but now I'm just going to do it again, was that we can make this connection to empirical risk minimization really tight by considering the logarithm of this object. Because Gaussians are exponentials of squares, their logarithms are just quadratic functions. So we can think of the posterior mean as the minimizer of the negative log posterior, the maximizer of the log posterior, which, if we write down the actual terms in these Gaussian prior and likelihoods, is the minimizer of a sum of two quadratic functions in theta. And that happens to have kind of this shape. So this is if we set theta to mu posterior, then we get a zero gradient here. And we also saw that the posterior covariance has another interpretation in terms of this log loss. Namely, it's the curvature of this log loss. And because quadratic functions have constant curvature, they span flat spaces, if you like, this covariance, this curvature, is constant for arbitrary values of theta. So it doesn't depend on theta. This is only true because of this linear assumption in the model. Because of this assumption, together with these Gaussian prior and likelihood assumptions. So, back then, I made a big spiel about why you want to be Bayesian. I showed that you can do all sorts of really cool things with these regression models. We did an example, inferred a really complicated function. I mean, it was one-dimensional, but it had lots of structure. It was periodic. It had individual additive and multiplicative components that we teased apart. We did source separation. We learned how to fit the hyperparameters of these models by constructing a strictly more powerful version of cross-validation that takes into account all possible cross-validations in one go using a determinant of a covariance matrix and various other things. So maybe a first question is, well, coming from this, you might wonder why should we still talk about deep learning? Because it seems like we had a really cool framework available there. But of course, you're not just in this lecture, you're also listening to the news. You know what AI is like these days. These algorithms that I presented to you early on in the lecture, like Gaussian process regression and Gaussian parametric regression, and also exponential families with conjugate priors, they may seem a bit quaint in 2025 because we have large language models and chatbots and amazing computer vision models and generative algorithms for images and so on, and they learn how to fold proteins and how to control fusion reactors, and none of them are actually Gaussian process regressors, right? So you could also turn this the other way around and say, why did we spend 10 weeks just doing Gaussian processes. Someone actually wrote in your feedback, is the whole thing going to be Gaussian? Like, when is the cool stuff coming? Well, so let's talk a little bit about why deep learning is actually good. So I know that, I mean, there's a sort of an emotional thing at the moment that the field has just decided deep learning is cool. So let's do deep learning and forget about all the old stuff. It's boring now. But I want to avoid doing that. I actually said already on Tuesday and then the week before as well that there are some good things in the old algorithms, and there's also some power in new deep learning frameworks. So what I'd like to do now, for a few minutes, is to highlight both the good and the bad aspects of the old stuff and the new hotness, and see whether we can salvage something from both ends, actually, rather than having to commit to one completely. Why is this a good idea? Well, because we just discovered in the last 5 minutes that they are very closely connected to each other. They are not fundamentally different paradigms. They are actually really close to each other. The only difference, arguably, between deep learning and the Gaussian models that I showed you is that there's a nonlinear function of the parameters in there. That's it. That's the entire thing. Now, unfortunately, that nonlinearity creates all sorts of challenges, algorithmic challenges, and interpretability challenges, theoretical challenges, that have needed some time for the community to get used to. And interestingly, the practical part of the community, the one that makes money, has been much faster picking up building software stacks, and the theory is only slowly catching up. So we're in a phase now, a little bit like in physics, when new experiments suggest that the old theory doesn't work anymore, and then the theoreticians have to come in and make some cool new stuff. That's also exciting. So first, let's think about what people actually like about deep learning. And let's not just say, oh, we like it because it can be AI, right? The large language models are cool. Yeah, fine, right? There used to be language models before deep learning. They just weren't as powerful. What is really the good thing about deep learning? So from a technical perspective, I would argue that there are maybe 3 central reasons that make deep neural networks good, apart from the fact that they perform well. The first one is that they are perceived to be O of 1 type training problems. And what I mean by that is that if you think about this empirical risk minimization that I introduced, there's this big sum in there. That's a sum over the entire training data set. So it's a sum over I from 1 to n, where n is the number of data. Now, what people regularly do, like it's basically so standard now that it's almost boring to say, is to subsample this sum. So instead of evaluating the entire sum, we're going to pick a few data points from the entire data. This used to be called mini-batching, where the entire batch is the data, but now the word has been a bit confused, and we talk about the batch as being the subset of the data. And then you compute this sum, and you divide by the size of the batch instead of the size of the data set. And then if you draw these elements IID from the whole set, which is easy to do because they're sitting somewhere on your hard drive, then this is an unbiased approximation to this thing. And the gradient of this, like the gradient of the loss, which is directly written here, is an unbiased approximation to the true gradient. And you can make this b very small. In fact, it's sometimes set to 1. And then you get a really cheap evaluation of the gradient. Of course, it's stochastic, so you pay a price for that, but it's very cheap. And so this is, I mean, I guess you're all aware of that, right? You've seen it in a deep learning class. But I find it useful to reflect on the effect that all of this has had. For example, just to highlight 2 points. One is that the theory of optimization died about 10 years ago. So there used to be a huge field called operations research with very proud members, people who thought of themselves as rocket scientists, who built super reliable optimization methods. Actually, not necessarily rocket scientists, that's more control engineers. The optimization people, they thought of themselves as quantitative economics people. Right? You can optimize every process, you can solve your supply chain management on a computer. And I used to go to lectures by people, in 2012, we had a lecture here in Tübingen by a very famous operations researcher. I'm not going to name a name because I'm going to be a little bit critical. And this person was completely confident. So all of machine learning is just an optimization problem. And here's like my big lecture on how to solve optimization problems. It's this theory about convexity and convex problems and like mixed integer programming and then constrained optimization problems. And then at some point he always had this running gag where he said like, once you've written down the optimization problem, how do you solve it? And then he waited for everyone at home to say something. And he said, it's none of your business because we've done it already. And there's these cool libraries that just solve every optimization problem for you. You never have to worry about it again. Once you have written it in the right form and you've shown that it's convex, it's all done. And that lasted until, I don't know, 2012 or so. And then suddenly, the optimization problem of computer science became this thing, and it's a stochastic problem. And none of these fancy methods work anymore. These old algorithms like LBFGS, for example, they scale to large problems. But they don't work on stochastic problems. They just don't. And so everyone somehow decided we don't need them anymore. Let's just do SGD or Adam a few years later. And Adam just emerged. They just got lucky. They were like one of the first slightly better algorithms. And then after that, there were like 150 other optimizers published, but nobody cared anymore because they had something that was reasonably good, Adam. And that's it. So now we've all just accepted that higher performant optimization methods don't really matter anymore. And it's just because of this noise. There's also another interesting development. That was that kernel methods somehow died. Right? We talked about Gaussian processes. And I showed you that they're really powerful, beautiful, mathematically beautiful tools operating in function spaces. Right? You can talk about these reproducing kernel Hilbert spaces and these Gaussian Hilbert spaces, reproducing kernel Banach spaces, wonderful functional analysis, universal learning machines. But they died, and why did they? Support vector machine, for example, as like the use case for these algorithms. And they're sort of gone. I mean, they're actually not really gone. They're still used in practice a lot, but they're not really the subject of research that much anymore because they're pretty much well understood. They work on problems of a particular size, and then that's it. So why did that happen? It happened because people had this conception that to train a kernel machine, you have to solve a least squares problem. And that means you have to invert a matrix. And inverting a matrix is cubically expensive in the size of the matrix. Well, if I have a lot of data, I can't pay cubic price. This is a boring problem now suddenly, right? I don't want to use this anymore because deep learning is linear in the data set size, right? It's linear, it's just one sum here. And actually you can subsample, and that's it, right? But of course, that's a complete misconception. Every step of the optimizer is linear or sublinear in the data set. But that doesn't mean that the convergence is going to be faster than a smart linear algebra method. So the problem here was a sort of a social one that people thought of, on the one hand, for linear algebra, these black box methods called Cholesky decomposition or SVD, and they were known to be cubically expensive. And on the other hand, you have these completely deconstructed algorithms that are stochastic and are just running around, right? They just make individual steps to do something good. But every single step is feasible. And you can scale to really huge data sets. This led to the emergence of this idea of array-centric programming. That was one word that was moved around for a while. That seemed to be popular for a bit. Another concept that's now popular is called single instruction multiple data, SIMD or SIMD. What's meant by this is this kind of structure, right? So you can think of computing the gradient of a loss for your optimization problem as constructing elements in an array like this. So you can think of an array of size, number of weights by number of data points. And then when you mini-batch, you subsample into the into the columns of this table, the blue bits here, sort of. And there's now cool software, like JAX, for example, that allows farming out this computation over hardware in a nicely abstracted way. So there are these VMAP and PMAP in functions in JAX, which allow you to just register a lot of devices. And if you're working for a fancy rich company, there might be a lot of devices that you're farming out to. And it's just one more line in your JAX code, or actually just one more decorator in your Python code, in the best case, where you just have like add PMAP, and suddenly everything gets farmed out to a huge data center, and everything runs like 100,000 times faster. That's pretty cool, and it's down due to this kind of structure. I still remember around 2012 or so when people got really excited about this. This was like a very sudden kind of development where people realized, oh, there's this cool software stack from NVIDIA now. We just have to write some nice wrappers about it, and then you can farm out, shard out, it's now called, into hardware. So that's cool. And then there's also an economic aspect that people quite like. Maybe it's not so prominent, but I think it is actually economically really important, which is that once you've trained a deep neural network, you have this big set of weights, of parameters, that you can keep secret. And then it's your secret model that you don't have to share with anyone. And you can serve the model by having people call the function, and it just returns the function. You can even sometimes share the weights in some cases and still limit what people can actually do, to which degree they can reverse engineer what you've done. Like witness this recent debate about DeepSeek and OpenAI, and like this, people were kind of excited that there's another startup that has managed to figure out what OpenAI has done magically, and they did release the weights actually. It's a public model, but you still don't know what they did to make it work. So that's kind of an interesting aspect. And it's not true for kernel machines. If you're releasing the weights of your kernel machine, you're releasing your training model, your training data, basically, right? Your training data, if you know the weights in your kernel machine, the training data is just one matrix inverse away, at least if you know what the kernel is. And you need to know what the kernel is, otherwise you can't call the kernel machine. But there are also other things that deep learning doesn't do well. And those tend to be what I would describe as convenience functionality. So what do I mean by that? Here's a few things that you don't really know how to do with a deep neural network. I mean, arguably, maybe you do know, but they're very like unwieldy to do. The first most obvious thing is to quantify uncertainty. If I've trained my deep neural network on 100,000 data points and it has 10 million parameters, it's clear that not all of these parameters are identified by the training data. But even if I have like a model with 48 billion parameters that has been trained on the internet, I don't know which of these parameters are actually confident and which are not. And then if I show this model a bunch of tokens and say, what's the next token? Sometimes it may be very confident about what the next token is, and sometimes there are many, many possible next tokens, and you just don't know. I mean, the model quantifies some sort of uncertainty by its predictive distribution, but that does not capture the uncertainty over the weights. So if you're running a large LLM, an LLM on some out-of-distribution text that it has never seen, it might actually just produce some complete garbage. And I mean, early on at least, before the engineers wrote all sorts of backstops, I guess we were getting used to these hallucinations from LLMs that just kept writing the same stuff over and over again and so on without the engine knowing that it's in a stupid state, basically. But maybe more prominently, something that's super hard to do with a neural network is to keep training. So if you have a trained neural network, someone has invested a few million euros or dollars into training some foundation model, and now you'd like to add some knowledge to this model. What do? Well, you just write down your loss function again, you add more data points, you compute more gradients, and then follow those gradients. And when you do that, what you'll find what happens is that the model starts forgetting what it was trained on. It loses performance on the original training set. And if you keep doing this for long enough, you'll get a really brain-dead model that has completely forgotten all the training data, or it has sort of messed it up. Let's compare this to, and so now, right now people have all sorts of cool tricks for this. Right? You've all heard about PEFT, parameter-efficient fine-tuning, and LoRa, and all these models. Right? There's like entire internet communities about them now. And they feel, to me at least, like a totally transient thing that we cannot live with for a long time. They feel very inefficient. Because compare this to our setting in Gaussian regression, where we discovered that you can keep training on multiple new data sets by basically writing a closure, a clearly defined software engineering concept around your Gaussian process. What do I mean by that? Let's be a bit more precise. If I give you, if I'm doing Gaussian process regression, just to remind you of the notation, with a first data set D1. So I'll start with a Gaussian process prior. on, over a function f that has a mean function and a covariance function. And now I get data that is a first data set, whatever. I'm going to train my foundation model, right? So I get some data set. Then because the Gaussian likelihood and the Gaussian prior are conjugate to each other, the posterior is again a Gaussian process. It's a Gaussian process with a new mean function and a covariance function, which I can think of as a new mu1 and k1. So it's just another function and kernel. So now if a new data set arrives, a second one, I just condition on this second data set by reusing this conjugacy of the Gaussian exponential family again. So I just compute a new update on the new data set using the updated kernels, k1, k2. And you remember all these pictures, right? It's completely obvious that I can take, I mean, I could have made a picture here for this, where you have a Gaussian process that has seen data points here, there, and there, and now I can add the data point there and there, and that won't mean that it will forget the old data stuff, the old data points. It will just keep everything in memory. And why can it do that? Because it has a kernel, and that kernel is effectively a sensitivity map. I mentioned when we did this lecture that you can think of the kernel as a sensitivity, as defining the gradient on the mean. So the model knows where it knows and where it doesn't know. Let me actually draw the picture, right? So if I start with the Gaussian process prior, then I get 3 data points, then I'll get something that looks like this, posterior. It'll have some uncertainty around it. Yeah? And now if I get more data here and there, then the model will adapt. It'll go up here, but it will still keep going through the old data points, and it will not forget. It'll just become more confident, right? And the mechanism we use to do that is this sausage of uncertainty, right? This posterior covariance that tells us what we already know and what we don't know, and where we should overwrite and how much we should overwrite. This has become completely impossible to do in deep learning. And now people do this lifelong learning, continual learning, parameter efficient fine-tuning, blah, 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 and so on. All of these are all invented new methods that are really awkward replacements for this clear mathematical formulation. Now, I'm not saying that people who came up with these methods are idiots. They're very smart. They're a good model. They're like the best we can possibly do at the moment. But this must feel very unsatisfying. I think where we are at the moment with this deep learning stack that we're now using is similar to like other domains in computer science in their early phases, where it was really awkward to do certain things because people had just about found out how to get the primary functionality out, and everything else underneath was really shaky. You're all most of you are not old enough to have used CD burners earlier on in your life. Maybe you know about CD RWs. And there was a phase when I was in high school when every half year someone in class had bought a new CD burner, and they were always, every half year they became twice as fast. But the more important thing was that every half year you could buy half as many CDs because they would not constantly eat them and burn them and destroy them anymore. They would just get more and more reliable because the hardware was getting better. Or those of you who lived through middle phases of Windows, they used to be operating systems used to constantly crash. You were working and like suddenly there was a blue screen. This has just stopped happening now because people have invested time to make things work. And there was all sorts of other functionality that wasn't available for a long time in various parts of computer science that has now become available. Even like early on, actually my favorite example of this is very early computers were basically typewriters, and there was no way to delete stuff once you had entered it. You had to type in an entire, like you typed in a line, and then when you pressed enter, it would print out the line, and that was it. That was gone, right? You had to use what you had written. My father used to have one of these old, just about computerized typewriters, where it had a bit of a short cache that you could type in one line. And then you had to hit enter, and it would print it out on a piece of paper, and then it was there. So you had a chance to correct your text while you were writing the line, but afterwards it was printed. Old typewriters didn't have anything like this. Once you made a mistake, you had to rip out the page and start again from scratch. Nowadays, on the top right of your keyboard, you have a delete button that allows you to remove things you've entered. Think about deep neural networks. They don't have a delete button. Once I've trained on a data set, and I've shown, I don't know, some generative model an image that I never wanted it to see, how do I get this image out of the network again? For example, here, what was it called? Stable diffusion was trained on a data set from the Lion initiative that contained all sorts of illegal images, child pornography, for example. And they are now all in this model. They're just baked in. How do we get rid of those again? You can't. You have to retrain the entire model. There is no way to say, please forget this. But we have this for other parts of, I mean, we know how to do this in a Turing machine, right? We can go into the memory and delete something. How do we do this for deep learning? We don't know. But maybe you can think for yourself how you would do this with a kernel machine. It's not hard. It's linear algebra. So kernel machines have a delete button, deep neural networks don't. And there's various other examples here. These are all things that are really not available for deep networks yet, that I would argue are super important to have. They're not on the same level, they're maybe of a different character to the raw performance. So if it really just comes down to doing the AI thing, deep neural networks are pretty impressive. They really work really well, and they're a lot better than kernel methods. They scale really well, they have been trained on very large problems, and so on. But, yeah, so here's the picture again. But in terms of their, let's say, convenience functionality, deleting stuff, adding stuff, tuning the architecture, deciding whether your network should have another layer or not, they really are not particularly easy to use. And also training, of course, is a complete nightmare, right? So one more point maybe to make. Something that we really don't know how to do well is how to select the data points. So, I mean, I mentioned this already in the regression lecture, that data loaders to this day are, I think it's fair to say, with only a little bit of simplification, effectively sampling IID from the training data set. So even the teams that train large language models at Google, at Facebook, at OpenAI, and all the other companies that do that now, they have these huge training data sets that contain pretty much the entire internet. And they do a little bit of like curriculum design, like they decide to train on Wikipedia for a while, and then on, I don't know which other data sets, right? But largely, it's just selecting uniformly at random from a large batch of data sets. While for GPs, we have this quantification of uncertainty that you can use to actively decide which data points are now important, even to actively decide which data points are important specifically for one task. And that's why algorithms like Bayesian optimization, for example, that some of you may have heard about, have become popular because they allow this sort of active design of experiments to select data points. They don't really scale to these internet scale data sets yet, but it's certainly something that one might want to work on. And as a step towards this, I'm not saying as the final answer, obviously not, because otherwise I wouldn't be here. I'd just be like making a few billion somewhere else. I'm going to, after the break, tell you that it turns out actually every deep neural network that you may use, every single deep architecture, actually is a Gaussian process. You just haven't written it down in the right way yet. And I'll tell you how to do that. It's just 4 easy steps that are already given away here. We'll do that after the break. And then I'll show you some code that actually does this, because it's actually possible to do that now. And on Tuesday, I will then explain to you why this is a good thing to have and demonstrate it. You can then get some of the functionality I just highlighted for Gaussian processes into deep neural networks, at least to some degree. We'll continue with that after the break. So before I start, I should say that what I'm going to present to you is, of course, like the work of many people. In particular, I'm going to base most of the exposition I'm showing you on a really, maybe the very first paper ever to think about Bayesian methods in deep learning in 1992 by David Mackay, called Bayesian interpolation. And there was a few papers around this year. That was his Annus Mirabilis. Maybe one of the reasons that these ideas haven't had much traction yet in the community is that this paper exists, because people feel like it's, over 30 years old, so it seems like an old idea, but somehow it has fallen out of fashion anyway. Some of the ideas I'll present to you are also effectively, they actually effectively come from now a small research community that is, I think, beginning to emerge around Bayesian deep learning. There are regular workshops at the main conferences that attract something like 1,000 people, but the core community is very small. There was a Darkstuhl workshop last year in November, organized among other people by MT Khan, who brought like 50 people together in a room. And what I want to highlight is that all of these people, I was there, agreed on the points that I made before the break, namely that this kind of functionality is needed and that it is valuable, that it has huge economic value, and there's basically money to be made with these ideas. We just have to wait for someone to figure out how to make the money. But they disagreed wildly, sometimes aggressively, on how to get this functionality working. So what I'm going to present to you is my personal take on how to get to do this. And my design criterion for this step is to find something that's as easy and as cheap as possible. It's specifically not to find something that works best. Because, as we'll find out today and also next week, there's actually a whole spectrum of algorithmic ways to endow deep neural networks with posteriors. You've now seen the math, right? We've realized that the training loss of a deep neural network is a log posterior. So that's it. That's the mathematical idea. We just have to get a handle on that posterior. And now people have come up with a whole host of algorithms to do that. Some of them are trying to find the most precise characterization of the posterior, to really create the true posterior. For example, my colleague Andrew Gordon-Wilson in New York is of that sort of conviction, and you can find his papers. He's investing a lot of computational resources into getting very precise characterizations of posteriors. What I'm going to show you is the other end of a spectrum of methods, namely that's guided by the idea of starting from where the deep learning community currently is, taking their results as a starting point, and then building an ever so lightweight posterior around it that just about gives you a posterior, an approximation that has probabilistic functionality and is as cheap as it can possibly be. And the price for that is that sometimes you get not so very reliable approximations. So that was the caveat I had to say beforehand. And now, having said that, I can go full-throated and just tell you every deep neural network is a Gaussian process. You just don't know yet. And how do we get that neural network? How do we tease that Gaussian process out of the neural network? Well, it's 4 easy steps that you see here on the back, on this slide. Let's go through them one by one. The first one is the most elaborate one: train your neural network. So that means you have to find the minimizer of your loss function. And how do you do that? Well, you do it in which way you like. So if you already have a trained neural network, great, you're done. Step 1 is already done. If you're a purist and you like stochastic gradient descent, go ahead and do it. If you like Adam, do that. If you prefer an Adam W with, I don't know, automatic tuning of the learning rate, also fine. It doesn't matter. You just find a point in the parameter space that you think works as a point estimate. In particular, you can also download a pre-trained model if you know the training data. You do need the training data, though. OK, so that's the first step. And that may seem trivial, but it's actually a really powerful idea to do things this way, because it means that you can start with something that works. Other methods that endow neural networks with posteriors tend to require a change to the training procedure. For example, they inject additional noise into the gradients to asymptotically sample from some probability distribution. Or you're reparameterizing the entire training procedure to optimize a probability distribution over the parameters. We're not going to do that. We're just training the neural network in whichever way you like. The second step is a conceptual one. It doesn't actually cost anything. It's just a thought process. So we will just realize that there is something there that we can use. And it's the following idea. We're going to linearize our neural network. And here I have to be very careful to make clear what I mean by linearize. We're going to turn this bivariate function, this second-order function that depends on parameters and inputs, into a linear function on the parameters, not into a linear function on the inputs. It will remain nonlinear on the inputs, but we'll make it linear in the parameters. And we do that with a Taylor approximation. So we're writing this function as the function evaluated at the trained weights. So that's f evaluated at theta star. That's a function, right? A function of inputs, and it's nonlinear in those inputs, plus the derivative of this function with respect to the parameters, so that's a Jacobian, times the distance in parameter space, times theta minus theta star. So important to notice is that this Jacobian you can compute. When I say every neural network, precisely what I mean is that this green object exists for everything that you are allowed to call a deep neural network, because if this doesn't exist, you can't train with backprop. That's the object that you compute with backprop, right? It's the derivative of the function with respect to the parameters. I'm going to simplify notation and call this phi. And it'll become obvious why I call this phi. The immediate intuition is it's something with features, right? It's to do with features. Okay? And now we think of this function as a function of theta. And you can see that this function is linear in theta, obviously. It's an approximation, right? I mean, there are higher order terms in this Taylor approximation that I just drop. And I'll call this linear function f tilde. This is called a linearized neural network sometimes by people like Alex Immer, for example, who has also contributed significantly to this line of work. But so far, we have really not done anything. We just know that this gradient exists, this Jacobian, but we haven't really used it for anything yet. Now comes a computationally demanding step, namely, we'll do Laplace approximation. We'll do what we did on Tuesday for linear models, but now we'll do it for nonlinear models. We will compute a second-order Taylor approximation to this loss function at the trained weights at theta star. And here, we'll suspend disbelief a little bit in various ways. So the first thing we'll do is we'll say, OK, a Taylor approximation has a constant term plus a linear term, but let's just say the linear term is 0. Why? Because we've trained the network, so we're at a mode, so the gradient is probably 0. It's actually not true that it's fully 0, because we've used stochastic optimization. It might not have converged yet, but whatever. We're just going to ignore that term. It's probably small. Plus a quadratic term, and that quadratic term involves the Hessian of the loss function. So it's a second-order derivative of the loss function. That means there is a matrix in there of size number of parameters by number of parameters. That's a huge object, right? So we're not mentally going to assume that we're going to instantiate that matrix. I'd like to ask you to think of that matrix in here as an operator, as some kind of ephemeral object, and we'll have to think about how to implement it on an actual computer, but we're probably not going to instantiate a quadratic matrix of size number of parameters by number of parameters, because it would require quadratic memory, let alone the compute cost to fill that matrix with numbers. Instead, we might do something like the following. You can write down the second derivative of the loss up here by realizing that in here, if we think of f as a linear function, right? So as we did on the previous slide, so we made this assumption that f is linearized, then you think of this object and compute the second derivative with respect to theta, well, then you will find by the chain rule that you will, hang on. So if you think of this, if you make the assumption that f in here is this linear function, Then let's take the second derivative of this loss. Well, we'll get first a derivative of the second derivative of the loss times the gradient of f with respect to theta. That will be our Jacobians, right? df d theta, plus, sorry, no, not df d theta, but dl df, right? So we first get dl squared times df, and that gives us the features, phi on the outside and the inside, plus a term that is a second derivative in f, right? So it's dl df times d square f d theta. That's what the chain rule says. And that second derivative is 0 because under this linearization, there is no second order term, right? The second derivative of this expression with respect to theta is 0. And then what you're left with is this matrix, which is called the generalized Gauss-Newton matrix. And I realize that it's a bit of a handful. It's a huge object. But we can look at it a little bit, and instead of doing chain rules and like wiggling around with algebra, we can think about the structure of this object. So this is a matrix that is indexed by parameters, A, B, so where A goes from 1 to D, the number of parameters. And then that matrix contains a sum over the entire data set from 1 to n, and then a second sum over all the outputs of our function f. So for binary classification, there's only a single output, or for regression, but for multi-class classification, there might be C outputs, right, for the number of classes. So for example, if this is an ImageNet model, there may be 1,000 classes that we're summing over. And then in here, you can see that if you just sort of squint with your eyes a little bit, you see that here there is a vector, and there's another vector, and this is an outer product between these vectors. And in here, there is a smaller matrix of size number of outputs by number of outputs. So if this is, let's say this is an MNIST model, there would be a 10 by 10 matrix in here for 10 classes, and then a large vector on the outside, for which you get an outer product. Or if it's an ImageNet model, then there's a 1,000 by 1,000 dimensional thing in here, and then there's 1,000 by number of parameters vectors out here, and then there is a sum over such expressions over all of the data points. This gives us the curvature of the loss in parameter space. We'll call this matrix psi inverse. It's the curvature of the loss in parameter space. And it's in red because what this object contains is the knowledge about the data set and how the model interacts with the data set. So on the previous slide, the blue thing is our point estimate. That's what people already have and use. The green thing is the Jacobian. That's what people have but don't really use at inference time. I mean, you use it during training, but then you don't use it at predict time. And this red thing is now a new object that doesn't feature in your normal deep learning. And it's a data structure that stores the information content of the data set for the model in the form of curvature. Right? Curvature of the loss. The loss is an object that contains the training data for this particular model f when evaluated at theta star. And we know from lectures, the last two lectures, right, that we can think of this as defining a posterior on the parameter space. A posterior Gaussian measure in theta land that is centered at theta star, the trained weights, and that has a covariance given by the inverse of this huge matrix, psi. That's in parameter space in theta. But we don't necessarily typically care about the weights. We care about the predictions of our neural network. So now comes the last step. We need to push this probability measure on the parameter space forward through our function f into the function space of predictions, of logit predictions of these networks. That's the corresponding step to what you are currently doing in your homework for linear models and what I discussed on Thursday and Tuesday for linear models. Namely, we're going to mentally do an integral and say, remember that we've assumed our function is linear approximately in theta space. Then we can write the probability density for f, actually the probability distribution for f, let's be a bit more careful, as a marginalization over, sort of as a push forward, right, from lecture 2, a push forward of a probability density. So we have this random variable called the parameters, which we have now identified with a Gaussian distribution. And we assume that our function is actually equal to this linear function. Gaussians are closed under linear maps, so therefore the associated probability distribution over the function f, this higher order function, is a Gaussian process. And what is this Gaussian process? So there is, and so this object is really sort of, we have constructed it mentally by just doing this integral on a piece of paper. We're not actually computing an integral here numerically, we're just thinking about it by making this linearization. We have a Gaussian process associated with our neural network, and it contains these objects, these blue, green, and red objects. The blue thing is the mean function of your Gaussian process. That is your trained neural network. So that's the thing you're already using. There's nothing new. It's still there. That's nice because you haven't lost it. It's still there. And around that thing, there is now a kernel, a covariance function. And this covariance function is actually what is called a degenerative kernel, right? So this is actually a parametric model. It has finitely many degrees of freedom. And you can think of this as a linear model with features, where the features are given by the Jacobians of the network with respect to its parameters evaluated at the trained parameters. This is the green stuff. Weighted by the curvature of the loss in the parameter space. So what this red thing says is how much you have learned about your parameters from the data. And what the green stuff tells you is how much that knowledge is used when I make a prediction on a particular new input. So if I want to make a prediction on one particular input bullet, this thing, then I just evaluate this kernel at one point. So I set the left and the right-hand side to the same thing. And then what this does is it says, let's pull back from the input, right? Let's check how much of the prediction, this prediction here, is based on which weight. Let's check how much I know each of these weights. That's what's in this red matrix here. And then project it back out to see what that means for my prediction. And so, right, if this prediction makes use of weights that are very badly known, then I'll be very uncertain in my prediction. And if that prediction makes use of weights that are very confidently known, then I'll get a confident prediction. That's the idea. So, any questions? Yes?
So this is very cool, but you introduced it as the focus is making it the cheapest it could be, and now an integral over the inverse of the Hessian.
Yeah.
That does not seem very
Great. So, there's the immediate obvious question, is just, isn't this expensive? So, let's briefly think about what, I can argue in both directions, right? My argument is that it's the cheapest possible thing, but also it's not completely for free. So it's the cheapest possible thing insofar as this is something you've already computed, no new cost. This is something you can compute with autodiff. So computing a Jacobian is at most 5 times more expensive than computing a function, the corresponding function. So it's a bounded cost overhead, backprop, right? Backprop is fast. You already have the infrastructure for it. It's called JAX or PyTorch. And then in the middle here, we have that matrix, of which I actually need to compute an inverse. You're completely right. And you know, computing inverses is cubically hard in the size of the matrix. Okay, so if you really want to do that, if you really build this matrix, then you're going to have to instantiate a matrix of size, number of parameters by number of parameters, and then you have to invert it, incurring a cubic cost, and that doesn't scale. But I haven't said that you actually need to build this entire matrix in memory and then call scipy.linalg.inf. So the name of the game is now going to be that we need to think about this red object and find approximations for it that capture a semblance of the curvature? This is a very good question. We could, for example, decide that we only care about certain blocks of that matrix. We could decide we only care about the last layer. Everything else in our network we're just going to ignore. We just put zeros everywhere. And then what that amounts to is to say we have actually we don't put zeros, we just ignore it. Right? Then what that amounts to is that we're just going to capture a certain part of the uncertainty. We could also say we're going to compute only the diagonal of this object. Then we need only linearly many parameters. It's probably going to be a bad approximation, but it's actually very cheap. It can be computed very efficiently. We could also say, maybe we can use all sorts of cool tricks. And then we discovered there's entire communities that are all about defining efficient approximations to matrices in numerical math, right? For example, the people who solve PDEs have all sorts of really cool structured approximations to matrix inverses. And then we can leverage all of their hard work from decades ago. And there is now an entire community of people that builds code for this kind of functionality. These are called curvature linear operators now. There are papers being published by people across the world and software libraries being built called curve-linops, for example, by Felix Dangel at the Vector Institute in Toronto. And there are there are also workshops now at conferences. There's one coming up at ICML where people basically build software libraries that work inside of this framework I just outlined to try and find smart approximations to this curvature. And that's a whole, like basically it's sort of autodiff on steroids, right? It's the second order, second life of automatic differentiation is to think about how to implement such operators. So to drive home that point, I'm going to show you some code, which is an example. And of course, I'm using my bully pulpit here to just show off our own stuff. There is a new library out called Laplace, which implements Laplace approximations, this entire framework in JAX. I'm going to show it to you in the next 15 minutes. It'll be initially published at a workshop at ICML in, 2 weeks from now, I think, or so, in Vancouver. But you can already install it now, pip install Laplace. And we're actually actively developing this in my research group, in particular by these people, by Tobias Weber, who you already, actually, have you seen him yet as a tutor? No, you'll see him next week, I think. Balint, you've seen in the very first week as a tutor. Lennart Rommel, who is a master student, and Thomas Christie is also a PhD student who you've seen. Lars and Marvin, who you all also know. And actually, they told me this morning that they would be quite interested in having Hiwi help them developing the software library if there is someone who is willing to dive really deeply into autodiff. It's a bit of a specialist field. It requires numerical linear algebra. It's very technical, sometimes a bit dry, but also quite rewarding because you don't have to wait for Adam to converge and decay the learning rate. You can actually, build some structured stuff. So let me know or let them know if you're interested. So here's the code that I want to show to you in the next 15, 20 minutes to highlight how this works. And again, I want to stress that there are other means of endowing deep neural networks with posteriors. A very simple one is called an ensemble, and that involves just training your network 10 times. And keeping all the 10 models around, or maybe 12 times, or 20 times, or 100 times, and then you keep all of these models around. And every time you make a prediction, you don't just ask one model, you ask 100 models to make a prediction, and then you just show all the predictions, and you pretend that they are samples from a posterior. That's a very easy thing to do. It's also, I would argue, expensive, because it means you have to store 10 models. There is no way we're going to get OpenAI to store 10 copies of ChatGPT. And every time one of you asks a question, we just ask all 10 of them and let them give you 10 answers and then average over them. It's just not going to happen, right? So if we want to have something that scales, we need to have a framework like this that at least has the opportunity to find some knobs that allow us to reduce complexity. And another nice thing about this is that it also keeps your old neural network. So if you already have a working ChatGPT, you can just build something around it. So how does this work? So I'm going to show you the entire piece of code. It's also on beat-up Jupyter Hub. Don't run it there, though. There is a problem with a more recent version of Laplace. They just released an early build, and so now it doesn't work on beat-up Jupyter Hub, but whatever. You can just download the code and run it on your own local machine. So what I'm doing here is, first of all, OK, I'm just loading a bunch of stuff. So far, I'm not loading anything interesting yet. Maybe one interesting aspect is that I'm using 64-bit precision, because that makes it's sometimes a bit of a safeguard to make computations more precise and reliable. Of course, that's not something we always want to do. Ideally, we'd actually like to use low precision, but let's not get ahead of ourselves. Now we do deep learning, and the entire story here now is going to be, by the way, can you read in the back? Is it OK with the font size? Good. So the entire story here is going to be that we just do deep learning. So we are going to use code that looks like deep learning code rather than writing our own solutions. So what you see here is sort of, well, again, I said at the outset of the lecture that people disagree on how to do deep learning, in particular in JAX. But this is just going to be my way of doing it, basically, which is partly taken from tutorials by the people who write these libraries. So there's a cell here that defines all sorts of constants, in particular also the architecture. We're going to use a multi-layer perceptron that takes in 2 inputs, maps to 128 neurons to 64 out to 1. Here's a bunch of things that you can immediately interpret. Then we define an architecture. Oh, by the way, I should run these cells so that they actually work. Now we define an architecture. This you've already seen on a slide, right? This is this multi-layer perceptron that I've defined before, which uses a definition of like how many layers do you have, initializes the parameters, and then afterwards you have a function. So that's our second order function. I give it a bunch of parameters, I get back a function. I've already run that. Now we construct our data set. You've already seen, and I'm going to be boring, and we use this 2 moons data set. Again, I know real problems are harder, but I want to make a plot in 2D, so whatever. Here's a quick 2D data set. And I'm already plotting underneath the point prediction. So this is the output of this classifier at initialization. It's just ReLU nonlinearities, randomly initialized with weights, and it's a typical sort of output for a ReLU classifier. It's piecewise linear, so far out here it becomes a linear classifier in any direction. But in the middle, it's just kind of some kind of mush of predictions. And now we define the training problem. And again, everything is as you would normally do. So we first define a data loader. In JAX, there doesn't seem to be some consensus on how to define a data loader. So we're going to use a data loader from Torch. If you've taken the deep learning class, maybe you've encountered something like this. So we're going to use, where is it, down here, the data loader. This is this object from PyTorch, which needs a collate function for how to make batches. And that's what I write up here. This is actually directly taken from a JAX tutorial by Google on how to build data loaders. So just copy-paste. Nasty piece of code, but just copy-paste. Then we need to decide on an optimizer. Here there is a library called Optax, which contains optimizers written by other people at Google who disagree on how to do deep learning. And for those, you have to define the important bit, the business end, the loss function. We've now realized that this loss function is a log likelihood. So we just write it down. And then so that we can track training, we also compute accuracy on a test set and on a train set. For that, we write functions. And then the important bit is that this Equinox library, this deep learning library, provides a filter function, it's called. And what this does is it takes a model, like this multi-layer perceptron, and then extracts the gradient and the value of the loss from this loss function when applied to this model on the training data that comes from a data loader on pairs of inputs and outputs. So that's the plumbing that constructs all the autodiff. So that's the magic where a lot of really important computations actually happen inside. A lot of things are being done for us, or prepared for us more precisely, that in the old days you would have had to implement. And you notice actually, if I run this cell a few more times, that this is very fast because it's lazy evaluation. It's just preparing data structures. And also initially evaluating a first batch loss on accuracy, and we can see that the initial accuracy is pretty bad, 50, 60%. It's good, so we can start training. Then we say which optimizer we're going to use. That's just a single line. Of course, we use Adam. And then we write the big training operation. And what that does is it takes in all the things that define our model, and then it defines a make step thing that basically wraps around, let's compute values and gradients of the loss, and then ask the optimizer to do its business, to work with the gradient to do the update. That's where the Adam update happens. And now we can do the actual training. So we just say, call this function, train, let it run, and it does. And here you see, whoop, took a bit of time. Now we're down to a train loss of basically 0. And the test losses are also very low because this is an easy data set. And here's our classifier. And it's arguably overly confident. It has found a good classifier for this network. For this data set. Blue up here, yellow down here. And it's a bit not so nice that, over here it seems super confident where the decision boundary is. But I mean, why would it need to be so confident over here, right? We really don't know whether the decision boundary is here or there, right? That's the problem with overconfidence of point estimates. So now, what do? Well, here's also, by the way, a training curve, goes down, is good. Now comes the actual, like the Bayesian stuff. So we load this Laplace library. These are these 3 lines. From this library, we're loading a curvature operator. So this is sort of the answer to your question, right? Someone has done a lot of work to create an interesting operator. There's a function there that operates on a deep learning model to extract the necessary quantities to compute curvature operators. In particular, the GGN, that's this generalized Gauss-Newton matrix that I had on the slide, for multivariate outputs. And now we run this. And also, what I'm also doing is, just for fun, I'm reloading again this Gaussian library that we've been lugging along with us for the entire course, because I really want to make the point that in the end you get a Gaussian process. So I'm going to turn this deep neural network into one of our Gaussian processes with our interface. And why is this cool? Well, because that library comes with all this functionality. It tells us how to make a plot, it can draw samples, you can multiply it with a bunch of features to do linear projections, and so on, right? All these functions that we've defined for Gaussians, they will suddenly become available once our neural network is a Gaussian process. Okay, so I've loaded this. And now, so the first thing is a little bit of Equinox magic. So remember that this model is a class that contains this data structure for how to map from the parameters to the function. So we'll need to extract this data structure so that the curvature operator can operate on it. And we do that, and you see that it takes no time. It's just extracting something that's an internal member of the class. Here's just something, if you don't want to use my Gaussian library, you can also just define your Gaussian process yourself, but you don't have to do that. And now here comes the actual Laplace approximation. So that cell does the heavy lifting. So what we do is we first say, what do you want to do the Laplace approximation on? I want to use the entire training set. So of course, one thing you could already use to speed up the process is to say, I'm only going to do the computation on a subsample data set. So I'm going to make this sum in the Laplace approximation much smaller. When you do that, something will happen to your uncertainty. So you should think about what exactly happens when you do that. But for the moment, we'll keep our life simple. We'll just use the entire training set. And then we tell this library to say, please construct this curvature matrix using this loss. I'll tell you that I've trained with binary cross entropy because the model doesn't contain this loss function, right? So I have to say this. This is the point where you're supposed to do your Taylor approximation, the trained neural network, on this model, which gives us all the autodiff. And this is the data that you're doing this on. There used to be a parameter here, which we don't need anymore. Then construct this covariance matrix. And here, I'm saying we'll do the expensive bit, because it's a pretty small model, so we can just do the full generalized Gauss-Newton matrix, which will be of size, number of parameters by parameters, but it's actually not instantiated as a matrix. It's instantiated as a matrix-valued object, a linear operator that you can then call later on. And then we need a prior, because to do Bayesian inference, you don't just do a likelihood, a Laplace approximation on the likelihood. You also do it on the prior. And here we're going to say we use an L2 prior, so a Gaussian prior with some precision. So that's the scalar in front, and we'll just set it to 1. It's actually an interesting question, and one of the design problems for these Laplace approximations, how to set that number. There are various algorithms now available for doing this. It's also very cheap to do this, because once you have this curvature matrix, just adding a scalar matrix is not that hard. It's just when you multiply with the thing, you just add a constant every time you multiply. But it's still something to tune. And because people actually decay their regularizer during training, you have to set that number. You can't just assume that whatever the user used as the last step is actually your prior. Then we define the kernel. So this is the function that does, actually, let me go back to the slide. So this is the function that does step 4. Right? So this step 3 was, step 3 is this line, and step 4, making the kernel, doing the integral in closed form, but it's analytic, there's no integral being computed, is this. It's just constructing the right objects. And then, of course, we just-in-time compile this so that it's fast to use later on. And then we're actually done. Now we can set up our Gaussian process. So we say a Gaussian process has a mean function and a kernel. So let's define the mean function. Let's define the kernel. Our mean function is just the trained neural network. And the kernel is a vectorization around this thing we've just constructed. And now we can call our own library, Gaussian process, and say, this is the mean function, this is the covariance function. Please do it. I'll run it. And now this takes a bit of time. Done. So this was the post-processing. Maybe it took here almost as long as training the network, or maybe a similar time. But again, we're using maybe the most expensive possible thing, the full covariance on this model, and it's just so that we can make a nice plot. And the rest is just plotting. So now I'm just running this to make a bunch of plots. And what you'll see is 2 plots that I also, they'll show up here in a second. If I actually have, did I actually hit enter? Yes. No, it's just, the rest is just matplotlib and drawing from a Gaussian, right? So I'm going to make plots where I draw from the posterior decision boundaries. And for that, I need a plotting grid. So there'll be a lot of points on the plotting grid, which will make a big Gaussian to draw samples from. And that means I need to build a big singular value decomposition from using this kernel just to make these nice plots. And here's what they look like. But actually, I have them on the slides as well, so I can show them to you. What you see on the left is what you would get for this data set if you don't do anything Bayesian. That's just your point estimate. That's the posterior mean function. The corresponding logits look like this, right? So that's the inverse of the logistic. It's just the same function, just without the softmax at the end. And now this Laplace approximation pushed forward through the nonlinearity produces this uncertainty quantification on the function valued prediction. So these are marginal standard deviations for each input. And if I combine this uncertainty with this point estimate, these two together, and push them through this approximation for the expected value of a logistic under a Gaussian that we had on Thursday, this approximation by David Mackay with a sigmoid of 1 mean over square root of 1 plus pi over 8 something, you get this plot over here. And now the first thing you can see is that the uncertainty is larger in this region over here around the decision boundary is sort of spread out, and it as compared to this one, right? And the model sort of notices that it's uncertain in these directions because they're not actually informed by the data. So if you can think of this mathematically, if you think of a point like here, now let me go back, like remember this point down here where we are uncertain, let's go back to the math. What happens here is that we put this point in here, this point in the grid here and there, and it says, oh, by the features learned by this neural network, we're asking to use parameters in the model that are actually not well identified. And so therefore, I'm uncertain in this region. Conversely, over here, I'm quite confident. And in particular, also far away from the data, here you see there's a little bit of confidence, and then it becomes more unconfident again, this model. That's an interesting question, what happens far away from the training data. We'll talk about that on Tuesday. And here are 4 samples from this distribution. And you can see they're all of this type that we are relatively confident around the training data, where what's blue, what's yellow. But outside, there's many different hypotheses. This is an extreme one, actually. I've got to be a little bit unlucky, where we sort of have a lot of blue. Here's one where we have a lot of yellow. Here's one over there. And these, I mean, they change a little bit with prior precision. But basically, the model now knows that there are regions of the input space that it doesn't know. Right? There are some parts where you just don't know. And we got this from a multi-layer perceptron just by measuring curvature. That's actually the end. Let me summarize. So first of all, I said, well, I made this bold claim, deliberately bold claim, that you can think of the logits of a trained neural network, the function f, the actual differentiable program, as a Gaussian process associated with a Gaussian process posterior when it has been trained on a data set, where the regularizer of the empirical risk minimization training is a log prior, the empirical risk is a log likelihood, the learned weights, the minimizer of the empirical risk, is a map estimate under this interpretation, and the corresponding model in function space is a Gaussian process where the trained neural network is the mean function, the curvature of the loss in parameter space, psi, is the covariance on the weights of an associated Gaussian distribution on the weights. And by mapping through the logistics, we get a kernel that is called the Laplace tangent kernel. And I'll tell you on Tuesday why it's called that way, that associates this model with a Gaussian process uncertainty on the outputs. And then I showed you that it's even possible to write code that does all of this. It's not just a piece of math. It actually creates an object of our Gaussian process type. So this lazily evaluated functional program that you can then instantiate later on and inherit all the functionality of Gaussian processes. The ability to draw samples, to evaluate at arbitrary input locations, later on lazily, to map through linear functions, to add together, to do source separation on, and so on and so on and so on, hyperparameter inference and so on. So on Tuesday, having made this construction, will not show you so much code, but instead just show you experimental results from papers to highlight that this functionality isn't just something that's philosophically nice to have, but it also creates actual functionality that you want to have in your deep neural network. So you want to be Bayesian in deep learning. Thank you very much.